All right, welcome. So in this video, I want to talk a little bit about attractors and feedback loops and how they apply to complex systems. So to start, I'll talk about a subfield of complex systems research called dynamical systems, which is a mathematical heavy field that studies the changes of a complex system over time, and we usually call these the dynamics of the system. In the field of dynamical systems, the concept of an attractor is going to be a state or a set of states towards which the complex system tends to evolve over time. The idea being that the system is attracted to this state or set of states. As a simple example, one complex system we could consider is a pendulum swinging, and the simplest attractor state for the pendulum would be the pendulum at rest. So I have a pendulum here from myphysicslab.com, and we are swinging this pendulum. This is a pendulum swinging with no friction, meaning it will repeat the exact same swing over and over again to infinity. However, if we increase the friction in the system, I'll turn it all the way up, then as we can see here, the system will be attracted to its attractor state, which is resting, as we see here. When a system is attracted to a single state, like the pendulum at rest, we call that a fixed point attractor. This is the simplest kind of attractor. Here's an image of myself and a bunch of my high school friends at one of my friends' wedding. In this case, we're all doing a jump, and that jump is to try and escape the attractor. The attractor in this picture is the Earth, and of course, the Earth is a fixed point attractor for any of us who live on it. Another good example of a fixed point attractor is a funnel. A funnel is a very simple machine that is used to gain control over a complex system. The complex system is the flowing of a liquid, and if we want to direct that flow into a particular location, a funnel will allow us to do that by using the fixed point attractor at the end of the funnel. We say that an attractor has a basin of attraction, and this is going to be the set of initial states that will evolve to that attractor. So in the case of our funnel, the sloped inclined plane is going to be the basin of attraction that directs all of the flow of our fluid down to the single attractor point. Here's another example of a basin of attraction. This is a bird feeder that any rain that falls into the basin of attraction will be brought into this puddle of water that will then be used to feed any birds that come by. Positive or negative feedback can occur when an event increases or decreases the likelihood of it occurring again in the future. We can put some of these ideas together here to see an example of a fixed point attractor plus some positive feedback that has been used to increase the basin of attraction for this fixed point attractor. This fixed point attractor is the Colorado River, and the basin of attraction for the Colorado River, any rain that's going to fall within the Grand Canyon is going to eventually end up in the Colorado River, and that's a depiction here. Now the positive feedback happens that we can imagine a long time ago. In geological terms, the Colorado River must have been just a very narrow river along the surface of the Earth here. But due to erosion, as the water flowed along its path, it would dig out a deeper path. That deeper path then would increase the likelihood that more water would flow down that path in the future, and thus creating a positive feedback loop. Over many, many thousands of years, that feedback loop has been able to carve away a very large portion of the American wilderness to create the Grand Canyon. Not all attractors are going to be fixed point attractors. In fact, most attractors are not fixed point attractors. It's more common that some of our attractors repeat a series of states, and if that's the case, we call this a limit cycle. The simplest and most obvious limit cycles that we have already encountered are the orbits of the planets around the sun, or the orbit of a moon around a planet. These limit cycles are also repeated at a microscopic level in the orbits of an electron around the nucleus of an atom. Here's another example of a cyclic or limit cycle attractor, plus a little bit of positive feedback as well. The formation of a hurricane is caused by the warm water in the ocean being sucked up into the atmosphere to create a spinning cloud. As this happens, if this continues over the water and there continues to be the same circumstances, more and more water will be pulled up into the hurricane, and of course this will continue to grow in strength and strength until the hurricane reaches land, at which point it will no longer be able to pull water up from the ocean and it will dissipate as it hits the land. This is an example of a very powerful positive feedback loop in Earth's climate system that can cause hurricanes, typhoons, cyclones, and tornadoes. Another cyclic attractor that is very common in the biological life on Earth is the attractors that coincide with the passing of the seasons in a given year. Now this is a very interesting cyclical attractor because it arises due to the interaction of a couple of other complex systems, in particular the rotation of the Earth and the Earth's orbit around the Sun. Due to the fact that the Earth rotates on a tilt, there's going to be a part of the Earth that is closer to the Sun at any given point in the year. If you're in the northern hemisphere, then during the summer months of July and August, we will be the closest to the Sun. If you're in the southern hemisphere, during the winter months of, say, February and March, you will be closest to the Sun. And this causes the change of the seasons, which is the warming of the atmosphere and the climate system of the Earth. That climate system responds to the position of the Earth relative to the Sun over the year. As inhabitants of the Earth, we call this passing the passing of the seasons, and it is a stronger passing if you are closer to one of the poles, and it is a more subtle change if you are closer to the equator. And all of the life forms on the Earth are adapted to this seasonal change so that they can go through seasonal changes themselves. A good example would be animals that engage in hibernation or migration behavior during the winters to avoid the cold, or the adaptation of our physical form, say the growing of a warm winter coat to keep us warm again in the winter. All of these adaptations to the passing of the seasons are part of what life has had to do to adapt to its environment. And that brings us to another example of a cyclical attractor, which is life itself. What I've got here is an image. This is a picture of Blue Ivy Carter and her mother, Beyonce Knowles, about the same age. And this is a composite where an image of both of these young women were taken together and put together, and we can see that there's a very, very strong familial resemblance between the mother and the daughter. And that's because life itself is performing a cyclical attractor over time, which is the birth, reproduction, and then death cycle that all living forms go through is another limit cycle in the process of a complex system. Life consists of all kinds of complex systems and all kinds of attractor states within those complex systems. This is a depiction of a genetic network, and then this is a genetic network from a flower. I can't recall which flower it is, but the states in the middle here, these states in the middle that is labeled with the attractor cycle, these are the healthy states that the genes of this plant will occupy during its normal healthy life cycle. And to put this to make this a little bit clearer, we can imagine each of these little dots here as being a gene, and let's for the moment assume that if it is white, that means that gene is turned off, and if it is blue, that means that gene is turned on. And you can see that for different assignments of genes turned on and off, we could end up in any one of these many, many states represented here by little circles. Now the healthy states are these 7 states in the attractor cycle, meaning that if we're in any one of these states, we will just move through these 7 states. Now this is common in a living system, that our life cycles, for us to maintain ourselves, we can't just do that sort of stationarily. We need to go through some kind of cycle, maybe eating, finding food, eating food, and expelling waste, for instance. That might be one cycle. Or another cycle that's very common that definitely maintains us is our heartbeat. Our heartbeat has to keep going, and there's going to be some cycle that's going to be controlling that as well. And that might be controlled by a genetic cycle. I believe your heartbeat is controlled by something something other than a genetic cycle. It's probably not genetics that are controlling it. Maybe it's your neurons that are controlling your heartbeat, but the same activity is at play here, meaning that we want to engage in this healthy cycle. Now, if your genes, if you're one of these plants and you happen to be outside of this healthy cycle, what this graph here is depicting is showing how this plant has evolved to respond to perturbances in its genetic environment. What that might mean is, say someone comes along, maybe a geneticist, and decides, hey, I'm going to go manipulate your genes and I'm going to turn some of them on and some of them off, and you're going to end up in this state up here. Well, what this genetic network says is that through a process of steps, you will eventually, this plant will hopefully return back to its healthy state and get pulled into this attractor cycle. And that's the idea of an attractor, is that while we're in any of these unhealthy states, that's where we don't want to be. If we've got our genetic system set up properly, then the healthy state should serve as an attractor for us to move back in. And this is sort of the basis of how some living systems are able to heal themselves or repair themselves when they are given some kind of noise or damage from their environment. Now, in the field of dynamical systems, we also like to study chaos and chaotic systems. And in that case, sometimes the attractor that we get is not going to be a simple fixed point or a simple cycle that is easy to observe. And in some of these cases, we might end up with an attractor that has what we call a fractal structure. And a fractal is something that has the same structure or repeated structure at different scales, or at all the different scales, meaning if we zoom in infinitely small, we will see the same structure. If we zoom out infinitely large, we will see the same structure. And this might be something, this is an example of that, is a snowflake, and a snowflake is formed, the crystal structure of a snowflake is formed due to the interactions of a complex system. What complex system is that? Well, that is going to be the water molecules. Now remember, the water molecules are H2O, 2 hydrogen and an oxygen. And if we actually look at what that looks like, when it forms into a molecule, the oxygen is actually a bigger atom and the hydrogen are smaller. And what usually happens is we get sort of one big bulb on one end and two little like ears, like a Mickey Mouse head, if you like, on the other end, where the two ears are the hydrogen atoms. Now what happens is in the water or in steam or in a cloud, those atoms are free to just move around, bounce into each other, bump off each other because they have high energy. They're in a gas state or a liquid state, meaning they can move around. But as that energy is removed from them, they cool down. As they cool down, they have to settle down into a state and they start coming to rest upon one another. And the way that these water molecules rest upon one another is dependent on their shape. So that little Mickey Mouse shape is important because the big oxygen atom has to align itself up with the two ears of the other water molecule. What that creates is it gives the water molecules the opportunity to arrange themselves in basically 6 different directions of axes, and we can see that that's actually happening here. But at any point, due to the interactions of these molecules as they are solidifying, as they are freezing and aligning themselves into this crystal structure, we might get 1 or 2 that are out of place, meaning they're unable to get into that structure, meaning they change the crystal structure by being, just being arranged improperly. We can fork that crystal structure so that instead of continuing along this axis, we might fork out along one of those other angles. And of course, those angles are being determined by our sort of 60 degrees here. That's the 360 degrees divided by 6, the 6 different angles that we could have here. Now, we can imagine as the snowflake is forming, these different crystalline structures might form due to minor changes in the way the original molecules are arranged in, say, the original liquid or gas state. And so that's why we say that every snowflake is going to be a unique shape, its own shape, because that shape is determined by the interactions of those molecules as the freezing happens. Now, the fractal shape is determined. We call the fractal shape an attractor, a strange attractor, because even though every snowflake is going to be different, there are there are amazing similarities between all of the snowflakes, that is their fractal structure, that we can see that that is the attractor state. That if we try and freeze up a new snowflake right now, there are things we can say about it. For instance, we're always going to see these sort of 6-pronged snowflakes. We're never going to see a 7-pronged snowflake, and that's because the attractor state for the freezing of water molecules is forced upon it by the way that the electromagnetics happen for those molecules. So this is one very common popular sort of fractal structure, is a snowflake. Another one we can look at here is the vein structure that appears inside of leaves, usually, or in other living things as well. We have a vein structure that appears inside our body as well. And this vein structure, as you can see in this leaf, has some wider veins, some sort of larger veins. We sometimes call these arteries that maybe carry a large flow of the nutrients to the different cells in the body. And then there are some narrower ones. They sort of branch out and branch out, and if we zoom in, that fractal structure is there. If we zoomed in, we would see that those branches branch into smaller and smaller branches. Why do we need to have this sort of branching structure inside of our bodies, or inside of vegetation's bodies as well? Is because we need to transfer the important nutrients, say for instance oxygen, to all of our cells. Those cells need them to do their normal cellular daily activities, and the way we need that is we need to transport them as though it's some kind of road network or transportation, maybe pipeline, that we can send those nutrients down. So the vein structure that is formed inside of, again, human bodies or inside of the leaves of a plant are formed by these vein structures branching out. Now, how did evolution come to the decision that it needs to branch out in this particular way? Well, again, the structure that we have here, this fractal structure, has arisen through the interaction, but the interactions of a complex system. But the complex system here is evolution. That over many tries, evolution has tried different kinds of vein structures, and evolution has selected, or natural selection has selected for the most efficient vein structures. And the most efficient ones are the ones that have this cool fractal branching structure, which means in this case we're talking about efficiency, meaning the least cost to build. So remember, the genetic machinery needs to build these veins and build these cells out. So the least cost to build for the most reward. So this maple leaf is trying to basically be a solar panel, make itself exposed to the light of the sun. So we want to have as much surface area as possible to be exposed to the sun, but also minimize the number of veins that we need to get nutrients to those different cells. And so evolution over many millions of years has selected for the optimal path, and that's what we see in the vein structures of this maple leaf, but also the vein structures of other living things. So here we have another example of a good complex system. This is the formation of a sand dune in a desert, and we can see if we look sort of closely down here at the bottom, we can see that there's these sort of little ripples or little rivulets formed in the sand. And this is formed due to, again, the interaction of a complex system. The complex system here is going to be the movement of sand particles as wind blows in the desert. Okay, now normally if you were in sort of a vegetated area like we see back here in the hills there, what happens is the plants and trees and such perform a very important purpose for the environment. That is that as the sand blows about, it will maybe smash into a tree and fall to the ground. So in that area, up in the vegetated area, it's hard to blow dirt around very much because it won't fly very far before it hits a plant and it falls to the ground. Well, that's not exactly true out in the desert where none of the plants can grow. Instead, what's going to happen here is we can imagine sand blowing back and forth from one of these ripples to another one, and what we can imagine is at least a likelihood that if one of these ripples is taller than the others, more little pieces of sand are going to crash into it as they're blowing around and fall and land on it. So we could imagine over time that the taller bumps here would end up getting taller, and the smaller bumps would end up disappearing and being merged into one of those larger bumps. Well, if that happens with, again, a process of positive feedback, we can get to a point where one of those bumps is so large it forms into a small mountain or a sand dune. And that's again, and again, if we go look here, this is fractal structure. We might think of this maybe as that a fixed point attractor. Well, if we go zoom in on that dune and we look really closely, on that dune there's going to be little ripples as well. So those little ripples, and again, if we zoomed in really, really close on these ripples, we would see that it's not perfectly smooth, it's rippled as well. And so this process, the fractal structure, repeats itself on various scales. We can zoom in and zoom out and we would see the same sort of rippling structure. And again, it comes or arises due to the interaction of sand particles blowing in the wind, and then the dune comes from the positive feedback of arising into a very large pile of dirt. So to look at another strange attractor, and just to revisit some concepts from our last video, in particular chaos, I want to introduce a double pendulum. So again, I've moved back to myphysicslab.com for this demo, and this is a double pendulum. A double pendulum is a pendulum hanging from a pendulum, and we can see here it's going through a little bit of a wobble. And we can maybe look at this wobble and it kind of looks like it's repeating the same wobble. You know, maybe it does sort of 2 wobbles left, 2 wobbles right, maybe. But actually, if we sort of narrowly look at it very closely, we'll see that each wobble is actually a little bit different than the previous one. And to make this a little bit clearer, again, at myphysicslab.com, they've added some extra help for us. So they've got this extra little graph here. Let's take a look at this graph. What this graph is actually plotting for us is the change of the angle of our two pendulums. And it's been going for a while here, so you can see that it's actually been tracing out a path inside this shape. Now this shape I would call a torus, and a torus is sort of like a donut shape if you were in 3 dimensions. But the idea is this double pendulum, at least the way that it is started from its initial conditions, will always be in a state within this torus, but which state it is well, it will trace out a trajectory along this torus over, it may repeat itself over some time, although it looks like thus far it has not repeated itself. It just keeps its wobble just wobbles a little bit different every single time, but the nature of the wobble is still something that is the attractor. That is, we can see here on the right-hand side that we never get one of these nodes wobbling way up here. It's doing a kind of just left and right, wobble, wobble, wobble. That's the form that's captured by this shape over here. So now the cool thing about a double pendulum is that it is a very chaotic complex system, and just like some of the orbits we saw in our previous video, we can show the chaos with just a very simple 3-body scenario. We have the pivot point and then the 2 different points of the pendulum. Now I've tried to put this perfectly straight up. It's not perfectly straight up because I'm not that good, but this is again to demonstrate sort of how we would do this in reality. This is a simulation, but you could set up this double pendulum in reality as well. And you could try and pull it straight up. Well, if you try and pull it straight up, you're probably like me. You're not going to be perfectly level. You're going to be a little bit to the left or a little bit to the right. That's fine. Your pendulum's going to fall as well. That's going to be the chaos. Remember, chaos means sensitivity to initial conditions. So a small change in initial conditions can make a very massive change in the behavior of the system. So let's take a look here. I'm going to try and play this system and just look at the wobble. See if you can predict it. So it starts a little bit slow, but the cool thing about the wobble we get here is that, well, it looks like that the inner one there was doing some loop-de-loops for a bit, but again, it loops around sometimes. Okay, it didn't get enough force to go all the way around. Oh, that time it did. Every time we can see the new behavior of it, and each new swing is going to be completely different than the last swing, or at least we don't know. It might repeat the same as the last swing, but that's the chaos of the system. And so maybe let's just take a look at the graph too. So this, I'm not sure if we could call this an attractor yet, because while we're still attracting out, or we're still tracing out some of the initial paths, it's certainly not as simple as that toroid that we just looked at. A toroid is sometimes considered to be more of a limit cycle-like attractor. It's got cyclical features to it, although it might still have fractal features to it as well. This one, I feel like if I let this go for a while, I should mention I don't have any friction in this system as well, so the energy in the system will be maintained, so it will never come to a rest point. And therefore, this might actually be a fractal attractor as well. This is something that we can see more as we let it run more to see if tracing out a particular shape here. And I think it probably is, and that shape might be fractal in nature. All right, I'll finish this video by just commenting on what is the importance of attractor states in complex systems. Well, one of the important things of an attractor state is that if a complex system is chaotic, then an attractor state is like a little pocket of order inside that chaos. So for instance, here this state again is still very chaotic, but if we had put in some friction, then it would attract itself to a point of rest, which would be a little piece of order inside this chaos. And what that means is if there's sort of a negative message from complex systems theory, which is that the universe is chaotic and we are unable to predict the chaotic behavior patterns of the universe, then the positive message that comes along with that is that the attractor states, these stable attractor states, fixed points, limit cycles, and even strange attractors, these form as little pockets of order within the chaotic universe that can move forward and maybe with goals and motivations to try and achieve things in the universe. That's what we are. We're a little pocket of order in this chaotic universe that has goals and motivations, and that's the other side. So there's a force of chaos that's maybe causing everything to sort of break down, but then there's also a force of order that's causing these little pockets of order to sort of self-organize inside these complex systems. All right, thanks a lot for watching this video on attractors and positive feedback. I'll see you in the next video.